Earlier in the semester for Lab 2, we were assigned to track the motion of a falling object while incorporating the drag force. And for that lab, the model for drag um, given to us was equal to a constant b, which was just a factor to help us better model the graph of a falling object multiplied by the velocity of the falling object squared. But in this lab, we take into account the mass. So a heavier object with the same surface area of a lighter object should fall at a faster rate equal to the square root of the ratio between the two masses. So 2 stacks of plates were dropped from a height of 2 meters in this lab. The lighter stack was made up of 5 plates with a collective mass of 0.0567 kilograms, and the heavier stack was made up of 25 plates with a collective mass of 0.2835 kilograms, which is 5 times heavier than the lighter stack. So in this lab, we used the model for drag to be equal to 1/2 rho v squared CdA, while Ft is equal to the drag force, rho is equal to the density of air at sea level, which is equal to 1.225 kilograms per cubic meter. V is the velocity of the falling object at that instant. Cd is equal to the drag coefficient, which is equal to 1.28, and A is equal to the cross-sectional area, which is 0.05446 square meters. I put this video into Tracker, and I tracked the object falling, and this is the lighter stack of plates, which took about 0.73 seconds to fall, and this is the heavier stack of plates, which took about 0.6 seconds to fall to the ground. So one can derive this velocity difference by equating the force of gravity equal to the force of air, and then you have the equation mg equals 1/2 rho v squared CdA. And when you algebraically manipulate both sides of the equations, you can compare the two answers, and you would eventually find that the heavier object falls at a rate of the square root of 5, or the ratio of the two masses. So I programmed I modeled this I modeled the situation in Python, and these are the initial conditions. I have the masses of the 2 stacks, and I have the initial positions and velocities, which are all 0, and the t is which is equal to 0. And then I have the iterative loop. So the loop went through, and while it was less than a certain number of meters, in this case 2, I would incorporate the drag force, or calculate the drag force, which is this, and I would also calculate the weights of each stack, and then you could find the net force of acting upon each plate, and then you can calculate the velocities and update the velocities and update the positions while you go through the loop. And when you reach the end of the loop, it would print out the time it took for the plates to reach the ground. So here are the results, and these are the tracker results. As you can see, the blue line represents how far the lighter stack fell, and the red based on time, and the red line represents how far it fell based on the time. And as you can see, as time goes on, the red stack falls at a faster rate than the blue stack. One can see that the drag force has more of an opposition to a lighter object, has more influence of how it falls compared to the heavier object. This graph shows the difference between the tracker model and the computer model, and the tracker model deviates a little bit from the computer model, but that's just because the force of drag has more of an effect when the object doesn't have that large of a mass, but it was still pretty close. And in this graph, you can see the comparison of the heavy stack of plates in tracker versus the predicted computer model. The model in this case predicted the real world results with a high degree of accuracy because the force of drag doesn't have that much of an effect on the falling stack of plates because it has a higher mass. So I followed up on this experiment to find out how accurate it was as time went on. So in this case, I had it fall 150 meters, and I predicted the time it took for the lighter stack of plates to fall 150 meters. In this case, the computer model predicted it to be 41.778 seconds. And then I divided this by the square root of 5 because that's a factor the velocities differ by. So in this case, it should be the same with time. And I calculated it to be 18.68 seconds. But then when I ran it in the model, it was equal to, the time was equal to 19.14 seconds. But it was very close because it's only off by 2.44%. So I'm going to run the code for you and see how it works. I set these, I set the time, or I set the rate to run very fast because we don't need to actually see how it falls or the comparison. But it predicts that the larger mass would fall at 19.14 seconds. So in conclusion, this new drag model predicts the the motion of a falling object very well and better than we did earlier in the semester.